Actually, let me just mute everybody. All right. So last time we talked about the vision and text multimodal learning, not just in medical domain, but in general domains. So as I said, since 2019, mid 2019, very similar architectures have been pouring out, which claims to do vision and text multimodal pre-training models. So even before that, like since 2014, 2015, people have been doing image captioning or conditional image generation or visual question answering, which can be seen as a multimodal learning, obviously. But the recent movement in multimodal learning is to use pre-trained model. So you pre-train a gigantic model all based on transformer, or specifically BERT, and you try to pre-train a BERT-based model with inputting vision and text simultaneously. And hopefully the model will start to understand the distribution of the image and text at the same time. So not separately, but at the same time. And then once you've pre-trained your model, you can fine tune it for various downstream tasks. Typically, mostly all the papers, like Uniter, InterBERT, VilBERT, VideoBERT, what else? PixelBERT, they all do visual, not all, but like most of them perform visual question answering, and maybe image to text retrieval or text to image retrieval. And we've seen the same thing. We've seen the same thing with chest X-ray and its reports. So you can do the same thing even without any domain knowledge. You can simply pre-train a BERT-based model with both X-ray images and its paired report, and we were able to see that the model was starting to understand what medical terms meant, both in terms of, like, grounded on pixel values. So we'll see similar thing today. So we'll see pre-training pre-trained multimodal model using graph and text. So why graph and text? It's we'll see one by one. So when we say EHR, typically we mean structured EHR. So it's either structured EHR or unstructured EHR, but the Mimic3 itself is obviously a structured EHR. So EHR is typically stored in a relational database, as I said many times before. So obviously there will be a number of tables, and each table would be responsible for storing some coherent information. So in case of Mimic3, there are patients table, admissions table, diagnosis table. There are I think there was 25 tables or so, and in EICU there were about the same number of tables, 25, 26 tables. So for example, as shown here, it would be like patients would have columns, and the tables would have columns, and they using the foreign key and the primary key, you can actually link a medical record of a single patient, or a medical record of a single admission, or a medical record of a single ICU stay, as much as it's based depending on what you want, or depending on what you want to link, or depending on what you want to construct as a training set, or a cohort study set. And as I said, again, relational database tables can be converted to a graph. So obviously here, if you want to do something for a patient named John, then you can look up the name John in the patient's table, and then see that his subject ID or his unique patient ID is 12. So you can start linking that, using the number 12 to link to the admissions made by John, and then the admissions would obviously have admission ID, and then you can use that information to see what kind of diagnoses or medications was John received during that specific admission. So if you convert this to a graph, then it would look like this. So here, instead of having to join different tables to make a consistent, coherent medical records for John, or for admission number 231, instead of having to join, you actually already have a complete graph that consists of all the knowledge without any overlapping information. So here, for example, subject ID John, subject ID 12, and admission ID 231, and those kind of stuff, or admission ID 231. They are kind of like duplicate information that is just distributed or separated in different tables. So we do that because we want to normalize the table, based on the normalization principle in database. So, but if we employ graphs instead of a table, instead of a bunch of tables, then you already don't have any. You already have zero duplicate information. You can just start from wherever you want. You can start from John, and then start hopping around. Go to here, go to here, go to here, and see what kind of diagnosis John received during this admission. So it's a bit more friendly towards knowledge inference, or embedding information. And when we say unstructured DHR, so usually unstructured medical records or unstructured DHR mean medical notes. So obviously, unstructured medical records also include medical images, EKG signals, or maybe like audio speech recordings. There are many different form or modality of unstructured medical records, but typically when people say that you need to consider both structured and unstructured medical records, they mean that you need to look at both the tables and the notes. And as I said before, in the medical notes week or medical notes session, medical text session, there are 15 document categories in the MIC3. So the largest among them, or the most frequent among them, is nursing notes, and then the next comes radiology notes, following. Oh, actually, there are two nursing notes, other, and nursing notes, and then ECG and all. And then discharge summary is right here. It's the sixth most frequent note category, and that's what you guys use for project number 2. And this is what we will use for graph and text multimodal learning as well. So discharge summary. So hopefully everybody's already super familiar with what discharge summary is. So some might ask that notes or medical notes are still structured because they are stored in a notes event table. So medical notes are still stored in a table. So there are columns, and there are contents of the columns. So partially you are correct if you were to claim that medical notes are structured information, because as like among how many notes, like among like a number of columns, this much is structured, like all the way until text is structured. So row ID, subject ID, hospital admission ID, the date that the text was entered, and at the time and sort time, yada yada yada, category, description, CGID, is error. Those are structured information, but this much is unstructured. So you can see here, this is row 1. So this one line here, like this one line, is a single entry of a notes events table, and it starts with row ID 174, subject ID 22532, yada yada yada. And starting from right here is where text column starts. And even though it consists of multiple lines, it is encapsulated with a double quotation mark. So it's a single value. So this single value, this much, is unstructured. So that's why we can technically call it unstructured DHR. And obviously, as I said, we'll only take a look at the discharge summary among 15 categories. So discharge summary, hopefully you've already took a look at the raw data many times. So that's the starting point of any data science. So you don't just dump your data into a machine learning model and hope it works out. You need to actually study the statistics, the distribution, the characteristics of the data before you start training your model, or you start designing your model for your task. So discharge summary consists of multiple subsections, so multiple headings. So there's admission date, discharge date, date of birth, sex, service, allergies. So a lot of different subheadings. And what you can learn from a single discharge summary note is obviously it is a summarization of your entire stay during the hospital. So it's not a summary for a single ICU stay. It's a summary. It's a summarization of the entire hospital stay. So anything that you as a patient experienced during a single hospital stay would be summarized in this discharge summary. So it's a high level. So it's a high level summarization. So, like, what was your main complaint during your? So obviously, I'm starting from the admission date and discharge date. So it's because this is a summary of the entire hospital stay. So you'll need to. The note will have to record when you entered the hospital and when you were discharged from the hospital, and then your basic demographic information and your past history, like what kind of allergies you have, what kind of complaint you had, and then starting from here is what you've experienced as a patient. So major surgical invasive procedures. So what kind of procedure you've received during the hospital stay, and history of a lot more patient history related to the patient medical conditions, and yada yada yada. And there are some lab results. So physical exam is part of laboratory laboratory tests, lab tests. So physical exams, so this is a part of a lab test results. And then there are some medication related information, like medications at admission, medications at discharge. And then so this, like these discharge medications, this information will be tied to the prescriptions table in the mimicry table, among the mimicry tables. And discharge diagnosis will be also tied to the diagnosis table in mimicry, among the mimicry tables. And I guess discharge condition, I guess some of them are all, only a couple of subsections are tied to a specific table, but all the other subsections are like, the information written in some subsections are scattered around the multiple tables in mimicry. So I guess we can actually take a look at yeah, we'll just take a look at one example. Right here, right? So let me reshare the screen. So this is a single discharge summary here. Okay, so it is a discharge summary. It is a discharge summary, and let me just readjust this, right? Discharge summary with row ID 177, subject ID 13702 at admission ID this. So yada yada yada. And as I said, it starts with admission date and discharge date, and there's a lot of information here. And what we are interested in today's topic is major surgery, so invasive procedure or major surgical invasive procedure. So here, during the hospital stay, this patient, whose subject ID is 13702, received these procedures. So this information will be present or will exist in the procedures table. So there was like procedures ICD-9, ICD table, and there was CPT table. So this information will exist in either of those two tables. So the patient went through intubation. I guess the patient was, had some kind of surgery. So, and arterial line placement. Something to do with artery, your blood vessel, I guess. PIC's line replacement, esophageal gastro duodenoscopy. I'm not sure what this even means. Something to do with your esophagus and your gastro. So it's like, 식도랑 위를 이제 이렇게 살펴보는 스코피니까 어떤 현미경 같이 이제 뭔가를 식도나 이런 거를 이제 이렇게 내시경 했다거나 뭐 그런 거겠죠 아마. 그다음에 arterial line replacement 이제 뭐 동맥에 있는 뭔가 무슨 뭐 시술해 놓은 거를 다시 이제 뭐 재조정했다 뭐 이런 거겠고 뭐 그런 거겠죠. 네. Okay, and history of patient illness. So history is, so if you're, unfortunately in Mimic3, all the history information about the patient is not recorded in a structured manner. It's only recorded in unstructured manner in the discharge summary. So that's a bit unfortunate. And if you go down here, there's past medical history and social history and pertinent results. So initial lab results. So the patient's white blood cell count was 14.1, red blood cell count was 4.20, yada, 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 a lot of information. And then starting from, I mean, a single discharge summary is such a lengthy text. And very brief hospital course. So what the brief experience, the medical experience the patient had over this hospital stay is that, you know, an 87-year-old female patient with no CHF's cardiac heart failure, congestive heart failure, COPD, complex I'm not sure what this is, chronic obstructive pulmonary disorder or something. So the patient has something, and then with a lot of discomfort or complaints, had stayed over several days with no intubation, with no SP intubation, but the patient did receive some kind of other intubation, as seen in the major surgical procedure. And medications on admission, discharge medications. So a lot of medications were prescribed for the patient at discharge. So the patient was on metoprolol, atorvastatin, folic acid, multivitamin, trazodone, melatonin, valsartan, albuterol. Like how many medications? Like starting from 1, this patient was on how many? About 22 different medications at discharge. So hopefully all these information, all these 22 medications would be present in the prescriptions table, because these medications were actually given to the patient, obviously. So, and diagnosis given to the patient at discharge was chronic COPD, so chronic obstructive pulmonary disorder, COPD, regulatory failure with intubation, respiratory failure. So because 이제 삽관을 했으니까 이제 호흡이 곤란하다, 그래서 호흡 곤란, and upper gastrointestinal bleed. So your gut is bleeding, or your upper gut, like, so the gut, 위가 이제 식도 연결돼 있으니까 이제 식도 윗부분이 이제 뭐 피가 난다, 뭐 그런 거고. Hypertension, 고혈압, anxiety, 불안증, and secondary diagnosis is coronary artery disease. So 이제 그 심장 쪽인 동맥이 뭐 질환이 있다. hypothyroidism. So 그 갑상선이 무슨 갑상선 기능이 저하돼 있다. 뭐 이런 거겠죠. So about 1, 2, 3, 4, 5, 6, 7. So 7 diagnoses were given to the patient at discharge. So hopefully we can find the same set of information from the diagnosis table as well. So yeah, you can kind of see what I'm getting at, right? So same information is the same set of information exists in both the discharge summary in an unstructured format and different tables like diagnosis table, lab result, lab test, lab table, prescriptions table, procedures tables. Same information exists in those tables in a structured manner. So obviously you would like to use both informations at the same time in order to capture what has been really going on to the patient during the hospital stay. So that's the motivation of doing a graph and text multimodal learning, or more specifically, not graph and text, it's structured and unstructured information multimodal learning at the same time. All right, so back to the slides. So here, so as we are already familiar with one discharge summary, there's one discharge summary per one admission. So this is an admission graph, just like, you know, you've seen the admission graph here. So we don't consider the subject, the patient table. So patient table, under the patient table, there will be multiple admissions, but since we're only dealing with one discharge summary at a time, so we will consider one admission at a time. So we're just looking at this level here, this much. So we don't consider this information. We consider only this information. So it's so this graph is a simplified graph, like from the graph that we've seen just like seconds ago. So under a single admission, there will be multiple procedures, multiple diagnoses, and multiple prescriptions. It's just that the figure only contains one of each, but there will be many, like, just like the patient that we've seen a minute ago. The patient received 7 diagnosis codes and 21 medication codes. So there should be at least 7 diagnoses nodes or 7 diagnosis entries, or 7 rows in the diagnosis table and 21 rows in the prescriptions table, which is the same as 7 nodes in here and 21 nodes in here. It's just that I've just drawn 1 nodes each. And under the diagnosis nodes, there would be diagnosis code, and the diagnosis code would actually lead to diagnosis dictionary table and the description of the code. I just simplified that, instead of writing a IC9 code here, I just wrote the actual description of the code. And under the prescription node, so that would amount to a single row in the prescription. There should be drug name, drug dosage, the starting date where you start to take the drug and date where you end taking the drug. So start date and end date, and then there will be drug type or drug routes or whatever. So there should be many different nodes actually underneath the prescriptions node. So here, so the admissions node is actually an empty node. It's just a row from the admissions table. So there should be, and this is an empty node because there should be under the admission node, there are already again like another, kind of like a placeholder nodes. So that diagnosis nodes itself, they don't mean anything. It's what's underneath the diagnosis node that counts. And the same goes for prescription nodes. Even though there should be 21 prescriptions nodes, each prescription node themselves are kind of useless. It's the literal nodes underneath the prescription nodes that determines the semantic of the prescriptions node. So the ones in the bottom are what really matters, and ones in the intermediate layer or in the top, they don't actually contain any useful information by themselves. So you need to embed these literal information to embed. So it's like a bottom up approach. You start embedding these, and then and then you derive the embedding of this, and then you derive the embedding of this, right? So anyway, so there's, as I said, there should be one discharge summary per admission. So this here is the sample discharge summary of this admission, and there are procedures subsection, and there should be a diagnosis subsection and the medication subsection. And hopefully, what we want to do is that we want to mix those two information together, like here and this and this. So this part is the structured knowledge with some information loss. So information loss being, for example, here, there could be some fine-grained information in the text, because those are written by actual human doctors. So, like the bilateral thoracentesis. I'm not sure what this is. Yeah, the procedures and surgical movements or diagnosis codes or discharge medication. The doctors could write even more granular information, like the code name. Instead of actually using the ICD-9 code, they have their own, knowledge of what they want to write. So when this information, when this fine-grained granular information is mapped to the tables, then there can be some information loss, but at least now we've gained the structuredness of the knowledge. So there's like a trade-off. So in this part, the knowledge, we gain access to structured knowledge. It's just that there could be some information loss. And this part is like a reverse trade-off. So there is fine-grained granular information existing in this text, but it is unstructured. So it's just, you know, a sequence of tokens, sequence of words, or sequence of subwords, and that's it. But it contains granular knowledge. So there's like a, you know, a trade-off between the two. So obviously, we don't want to use only one information source or one modality. We want to use both modalities at the same time, so that, you know, they can act like a complementary information. So that is the motivation behind wanting to use both structured and unstructured information source, or specifically graph and text multimodal learning. So what can you? So as I said, graph and text can complement each other, and you know what do we want to do once we pre-trained a pre-trained a model for multimodal learning using graph and text. So what is it good for? So first of all, we want to see if the machine can actually ground words to a given structure. So previously, using the vision text multimodal learning example, we were able to see that the machine can ground words to pixels. So that was an interesting phenomenon. And we want to see the same thing, see if the machine can ground words to a graph, or the nodes in the graph. So it means that the structure is already given. So no, we tell the model that there is a certain structure with, you know, multiple nodes and edges, and, you know, edges and hierarchy, and that structure has something to do with the given text, and that's it. That's all we are going to give to the model, you know. And then by looking at thousands or tens of thousands or hundreds of thousands of example graph text pairs, hopefully we want to see the model starting to understand how to map certain portion of knowledge in the text to the graphical structure. So that is what we want to see. And if the model can successfully do that, then we can perform a lot of multimodal tasks, such as, you know, graph condition, text generation. So given a graphical structure, we want to map that to we want to generate unstructured text from the graph, just like we were able to generate text from the medical image, chest X-ray image. We want to do the same for the EHR graph. So given an entire admission structure or graphical structure, we want the model to write a discharge summary. And, you know, aside from that, there can be a lot more tests can be done, such as like error detection in text, or error detection in text, or error detection in the graph as well. Like if there's a typo, then you can use one modality to see if there's a typo in another modality. So we can do error detection. So that is why it's a good idea to use multiple information sources at the same time. If you only use one information source, then, and there are typos, or there are errors, or there's missing information, then you have to deal with it. There's no way to cope with it. But if you have multiple information sources, then you can rely on other sources of information when you see some kind of like doubtful information entry. Like if there's you know, a person's weight is entered like 1,000 kilograms, then that is obviously a typo. So you can actually try to recover the original, like actual value from text, or you can do vice versa. You can do the same thing as image text retrieval. You can do graph text retrieval, graph link prediction. So for example, based on a given text, you want to see if there should be a relationship between two nodes in the graph, or you know, do a node prediction as well. So given the text, you want to see if there should be a node in the certain part of the graph, and if so, then what kind of what identity the node should have. And obviously, you can do multimodal classification as well, given graph and text at the same time. You know, try to predict the future disease, or try to predict the future medication to recommend, or something like that. So you can do a lot more with two modalities than you can do with one modality, obviously. So let's say that we're going to use a two-stream architecture. So we have a graph and we have a text. We have graph and text, and we want to mix those information together at the same time. So if you remember what we've done with the vision and text input, we first encoded or embedded the image with a image encoder, which is basically resident or any convolution. So we first pass the image to a convolution, and then we obtain a set of image fibers, basically image feature maps, so set of image fibers, and then we start putting them into the BERT architecture along with the text tokens, right? So you can do the similar thing here as well. So each modality will have its own encoder. So for graph, obviously we want to have a graph encoder, and for text we want to have a text encoder. And then once we've embedded them into, like, preliminarily to a certain tokens or certain embeddings, and then we put them into the next layer, which is cross-modal encoder. So here, once we have the embeddings from the graph encoder and the embeddings from the text encoder, we put them into the BERT type architecture here. So it's like a cross-modal attention is going on. Just like if you remember the decoder of the transformer, there's encoder-decoder attention on top of the self-attention block. So this is the same thing. So here, when the graph encoder or the embeddings from the graph encoder is attending to the embeddings from the text encoder, then this will be the key, and this will be the this will be the query. This will be Q, and this will be KV. Conversely, if the text encoder output is attending to the graph encoder output, then this will be Q, and this will be KV. So it's like cross-modal attention going on at the same time for both modalities. And once you've mixed them together, then we do a couple more self-attentions, and then we finally have a set of contextualized outputs for the graph nodes. So all the admission nodes, procedure nodes, diagnosis nodes, and the literal nodes, they will be all here. And this part will have contextualized embeddings for the text. So all the text, all the subwords from here will be here, right here. But they will have been contextualized based on both modalities at the same time. Right. So yeah, we want the graph neural, obviously for the graphing, when you want to encode the graphical information, we want to use graph neural networks. This is natural. And for here, we want to use, obviously, transformer encoder is enough. Just like BERT, just like how BERT is using a layer, like multiple layers of transformer encoder. Here, to encode the text, we will simply use a couple layers of transformer encoders. So this part is interesting. Actually, this part is straightforward. This part is interesting, right? Because what kind of graph neural networks do we want to use? There's like graph convolution network, there's graph attention network, there's like GIN, there's like, oh, it says that my internet connection is unstable again. Okay, so I think it's okay to go on. So yeah, a lot of graph neural network variants, and what kind of graph neural networks do we want to use? And it's actually up to you. You can use whichever graph neural networks you want to use. But here, we'll focus on the similarity between transformer and graph convolution, and try to make the architecture as as coherent or homogeneous as possible. So that's why we want to focus on the similarity between transformer and graph convolution, or specifically self-attention versus graph convolution. So those of you who attended my class in the last semester in programming for AI, we covered how, after studying transformer and after studying graph neural networks or graph convolution networks, we covered how they can be seen as the same as how they can be seen as coming from the same family function. So it's like they're like the same thing. It's just that one, like graph convolution, comes from using a fixed adjacency matrix, and self-attention uses attention mechanism to determine the graph adjacency matrix. So we'll briefly refresh on. We'll have a brief refresher on that. So transformer attention, transformer self-attention, the so-called QKV operation, or the scale dot product, looks like this. So there's softmax QK transpose divided by the square root of the dimension size, and this is multiplied by matrix multiplied by the value matrix. So if we consider there are 6 tokens in your input, so I like going to movies, termination symbol, then softmax, this part, softmax QK transpose, this part is how you derive or how you produce a normalized adjacency matrix or normalized attention map. So here, this row should sum to 1, and this row should sum to 1. Oh, there's a typo. This only sums to 0.9, but that's a typo. So this should be 0.2. So this sums to 1, this sums to 1, this sums to 1, and the strength or the values in each dimension in each row determines how much you want to mix different tokens to arrive at the final output. So here, if this is 0.5, 0.1, 0.22, that means that you want to, when mixing mixing the different tokens here, you want to mix 50% of this token and 10% of this embedding and 20% this embedding, 20% this embedding. So this line here or this row here is how the token I wants to attend to all the other tokens. And similarly, this line here, this row here is how the token like it wants to attend to all the other tokens, right? So on and so forth. So this is self-attention. And graph convolution, hopefully everybody's familiar with graph convolution formulation. So a single graph convolution layer consists of a D inverse A prime, which is normalized adjacency matrix. And XW is just, it's node embedding, XW. And then when you multiply the two and then put it through a nonlinear activation function, then that's how you derive a node embedding for one layer. And if you look at inner working, so D inverse A prime is, as I said, it's a normalized adjacency matrix, and the adjacency matrix, the diagonal elements are all filled in. It's not zero, so that you have a self loop. So let's assume that you have a graph that looks like this. So it's kind of hierarchical, and then you add self loop here. So every node has a self loop. So there's like self connection here, self connection here, 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 here. That's why we have all the diagonal lines with non-zero values, and they're normalized so that each row sums to 1, sums to 1, sums to 1, sums to 1. And so you can see that this D inverse A prime reflects reflects the structure of the graph here. So 1 is connected to 2, 3. So 1 is connected to 2, 3. 3 is connected to 1, 4, and 6. So 3 is connected to 1, 4, and 6, and there's a self loop. So once you matrix multiply this matrix with this node embedding, and then you get this. And what you arrive at is just how you want to mix the nodes together. So for the first node, you want to mix this. You want to mix 1, 2, 3 node number 1, 2, 3, and this is how you arrive at this row. And for the row number two, you want to mix 1 and 4 and 5, and this is exactly what's happening. You're mixing 1 and 4 and 5 and itself. So that's how you arrive at this row, and yada yada. The rest is the same. So if you compare this and this at the same time, then you can see there's like very tight connection between the two. It's obviously here. This is a normalized attention. This normalized attention map and this normalized adjacency matrix is the same thing. It's just how much you want to mix different embeddings. It's either the different token embeddings or it's either different node embeddings. How you want to mix them together to derive a new contextualized embeddings here and here. So if you compare for the mathematical formulation of the two, so graph neural networks, you have a D inverse A prime here, which is the normalized attention map, and CW is a node embedding. And in transformer, you have softmax QK transpose, which is a normalized attention map, and this is the node embedding. So there's one-to-one mapping here. So this much and this much is the same. It's just that this much is fixed and this much is learned. And this much is node embedding. And V here, V is this. They're the same node embeddings. So if you compare self-attention versus graph convolution, in self-attention, you assume that you don't know the graph structures. Obviously there is something going on in your sequence input. So your sentence. So if you're familiar with NLP, NLP background, there's something called dependency parsing. So in dependency parsing, what you want to do is you want to parse a given sentence so that you can figure out the like a hierarchical tree like structure in your sentence. For example, like if you have like a pretty girl is walking down the street, then a pretty girl is like it's a noun phrase. Okay, 명사 구죠. 이제 예쁜 여자는 명사 구고 뭐 walking down, walking은 이제 pretty girl, 그러니까 is walking은 뭐 동사구고, 그다음에 down the street이면은 그 뭐 부사구고, 뭐 이런 식으로 이제 다 이 파싱을 할 수가 엮어가지고, 그래서 이제 뭐 명사구는 동사구는 이제 동사구는 부사구랑 붙어가지고 다시 또 뭐 더 큰 단위의 동사구가 되고, 그 다음에 이제 명사구가 다시 또 그 더 큰 동사구를 써서 이제 어떤 전체적인 어떤 센텐스 이제 문장구가 되고, 뭐 그런 식이 뭐 되는 거거든요. 이제 그 파싱이 그거를 이제 나는 뭐 이제 그 정확한 스트럭처는 모르겠지만 내가 이제 이 셀프 어텐션을 통해서 그걸 찾았으면 좋겠다라는 어떤 가정이 깔려 있는 거죠. 이 트랜스포머를 할 때는. So you don't know the exact parsing structure, but you kind of want the transformer to learn the parsing structure. So that is why you want to use self-attention. So you don't know the graphic structure, but you assume that, and you assume that the graphs you assume all the tokens are fully connected in the beginning. You assume that they're all fully connected, and then you learn the edge weights as you go, as you train your model. So that it means that you're learning the node embeddings in a data-driven fashion. So the adjacency matrix is determined by the attention mechanism, which is determined by a learnable parameter. So it's all data-driven. And in graph convolution, you do have prior knowledge on the graph structure. So you know the exact graph structure. So you just have a fixed graph structure all the way. So you just use the same D inverse A prime at every layer of the graph convolution. So if you do one graph convolution, that means that you're aggregating information from nodes that are one hop away. And if you do two graph convolution twice, if you perform graph convolution twice, then it means that you're aggregating information from the nodes that are 2 hops away, and then 3 hops away, 4 hops away as you go. So yeah, so you're learning the node embeddings based on the fixed adjacency matrix. So one is pure. So self-attention is purely data driven, and the other is purely prior knowledge driven. So if you arrive at this decision, the similarity between self-attention or transformer and graph convolution, then you might want to tune or modify your transformer architecture so that it behaves like a graph convolution, a graph encoder. So you can actually simply tweak the transformer encoder minimally to make it act like a graph convolution, because a transformer, it just, the transformer architecture looks like this. There's self-attention here, and then there's feed-forward network that comes after the self-attention. And I'm just omitting all the residual networks and the layer normalization terms. Layer normalization operation is just, in essence, it's like this. And graph neural networks are also, in essence, it looks like this. Once you do graph convolution, then you push the node embeddings through multiple nonlinear feed-forward networks. So even the NLPs are the same. It's just that internally, these much are different. But again, there's like one-to-one mapping between the two. So you can minimally tweak transformer to make it act like a graph neural network. So how are we going to do that is based on here, the mask self-attention. So if you remember the encoder decoder architecture of transformer, there's a mask self-attention here at the beginning of the decoder layer. And what this amounts to is just simply manipulating your attention map. So how we do it in the decoder self-attention is that we used masked self-attention because we wanted the decoder not to, so we wanted the input tokens to the decoder only attend to the past and itself and not to the future, because the transformer decoder needs to generate the tokens auto-regressively. So the input tokens in the decoder cannot look into the future. That would be cheating. So just like here. And decoder is okay. In the decoder, you're already given a sentence, so you can fully attend. Like the tokens in the decoder the tokens in the encoder can fully attend to all the other tokens bidirectionally. But in the decoder, the input tokens can only look at itself and the past. So for example, I can only attend to itself. It can never attend to the future. M can attend to itself and I. A can attend to itself and M and I. Student can attend to itself and A and M and I. So the attention never goes to the future. So in order to prevent that from happening, in order for the decoder to only attend to it, in order for the input tokens to the decoder only attend to its past, you need to have a special mask here that looks like this. So before you do the softmix, you want to multiply your QK transpose with a triangular matrix that looks like this. So the lower triangle of this matrix is filled with 1, and the upper triangle is filled with negative infinities. And when you multiply this with the QK transpose output, then all the other, all the upper triangular, so the upper triangle of this will be filled with negative infinity, right? And once you apply softmix to the negative infinity, then those parts will have zero probability. So only the lower triangle would have non-zero probability after the softmix. So that is how we manipulate the probability, or that's how we manipulate the attention map with the mask. So the mask QKV operation would look like this. So if this is your, again, the same input, then all the upper triangle would be filled with 0. So this is already, so this part is after this softmix. So it is already normalized. So the rows should sum to 1 here, sum to 1, sum to 1, sum to 1. Is that the upper triangle are forcibly assigned 0 probability thanks to the negative infinity mask. So in the same manner, given a graphical structure that looks like this, instead of using a fixed normalized adjacency map using the D inverse A prime, we can do this instead. So we can actually prepare a masked matrix filled with 1s and negative infinities, and then multiply that to QK transpose, and then apply softmix to arrive at this matrix here. So the rows would sum to 1, 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 and only the nodes that are connected to each other are assigned non-zero probability, and the specific values of the probability is determined by the self-attention process. So it's no longer fixed like 0, like 3, like a third, a fourth, 2, 5, 2, 5, 2, 5, 3, 3, 3, 5, 5, 5, 5. It's no longer like this. So it is dynamically generated on the fly based on the QK transpose operation. It's just that we only want non-zero attention probabilities to connected nodes. So once you do this, then you simply matrix multiply this with V, and then this is how you do graph attention. So this specific operation was already not exactly this, but similar idea was proposed in graph attention network in 2018 iClear paper. So the exact formulation is a bit different, like how they arrive at the attention strength. They don't use QK transpose. They don't use QKB operation. They use their own, attention generation function. But spiritually, the essence is the core principle is exactly the same. You use a mask to mask out a certain portion of your matrix, and then assign non-zero probabilities for the remaining connected nodes. So that's how we can simply introduce this one particular matrix here, and that's how you change your transformer to a graph attention network, or graph attention transformer actually, or maybe you can call that graph transformer. So here, both graph encoder and text encoder are now implemented based on transformer encoder. It's just that Graph encoder uses mask detection, and that's it. That's the only difference between these two architecture. So you can, so the entire model can simply be implemented based on transformer. So that makes the job of the researcher easier. And transformers are super efficient architecture. I mean, when you push it through like a large scale GPU servers or TPU servers. So yeah, that's it. So that's as far as the model goes. And obviously, we want to pre-train this model, so there should be some pre-training tasks. And specifically, we can come up with 4 representative pre-training tasks. So if you remember, in vision text, there was all the tasks, all the models like Uniter, Interbird, Pixelbird, they all use at least 2 pre-training tasks, which were 1, mask language modeling for the text embeddings, and 2, image text matching using the CLS embeddings, right? So here we can do the same thing. We can use mask language modeling here. So we randomly mask the certain portion and then try to reconstruct this identity. So there's mask language modeling for this part, and then there's graph text alignment loss here in this part. So there's like CLS embedding here and CLS embedding here. You simply concatenate them two and then push it through like a linear layer to see if they are aligned or not, if the graph and text are a matching pair or not. And then for the graph part, so unfortunately, we can do similar things as ML mask language modeling. For the vision part and vision text, especially in Pixelbird, we weren't able to do anything similar to mask language modeling for the vision embedding because each vision fiber, we couldn't assign anything to the vision fiber. In Interbird, in Uniter, in Vilbird, the images were first pre-processed using an object detection algorithm using specifically faster RCNN. So each image fiber already had its own class. So that's how we could use similar thing like MLM. But in Pixelbird, there was no object detection algorithm used. So each pixel fiber wasn't assigned a specific label. So we couldn't do anything similar to MLM. But here, the nodes already are assigned specific values. So, like this is a specific medication name, this is a specific diagnosis name, this is a specific procedure name. So at least for these literal nodes, or at least for the edge nodes, we can put a mask on it and then try to recover its identity. So that's what it's called that's why it's called masked literal prediction, MLP. So we only mask out the literals and then try to predict its identity. And one more thing we could do is based on we're exploiting the nature, the characteristics of the graph data. So graph consists of both edges and nodes, or relations to be more specific. So edges or we can actually use edges or relations as a pre-training objective. So here, what we do is we try to predict whether a certain pair of nodes are connected to each other, and if so, what are the identity of that relation. So here, the edge between admission and procedure should be procedure order, and the edge between admission and diagnosis should be a diagnosis order and prescription order. And then here, for example, between this drug name and prescription node, the edge here should be a drug name edge, and this should be drug dosage edge, and this should be drug routes edge. So we can try to predict whether a set of nodes like this and this, what is the identity of the edge between the two, and obviously it should be drug routes. So this is a relation classification. So we randomly choose 2 nodes from the contextualized graph nodes and try to see if there should be a node, what is the relationship between those 2. So most of the time it would be none, because like this guy and this guy is not connected. This guy and this guy is not connected. So most of the time it would be no relation. So using these 4 pre-training tests, we can simply pre-train this model and then use it as and then hopefully that will be enough to that'll be enough for the model to understand the relationship between the text and the graph. All right, so in order to see if the model actually understood the relationship between the graph and the text modalities, we can do 4 downstream tasks. So one is obviously retrieval. So just like we did image text retrieval, we can do graph text retrieval. So given a graph, try to recover the most relevant discharge summary, or given a discharge summary, you retrieve the most relevant admission graph. And similar to the report generation, we can do clinical note generation. So given a graph, we want to generate a discharge summary. And medication prediction is given only a partial information like this, we want to predict whether it can, we want to see if the model can predict the medications. And error detection is what I briefly described previously. So in error detection, there can be many, usually what happens is the report is first generated and then it is mapped into the table. So there is someone who enters this information into the EHR relational database. So in that process, there can be some errors. Like, for example, like you would use different unit, like wrong unit of measurement. Instead of using centimeter, you would use meter. Or if you, instead of using Celsius, you can use Fahrenheit, something like that. Or you can confuse the decimal point location. Like instead of using 0.0, instead of writing 0.1, you can write 10 or 0.01, something like this. So what we want to do is, based on the original text, see if we can find a error node in this graphical structure. And so we can actually inject intentional errors into the nodes, and then see if we can see if the model can find the errors actually based on the text. So we can do about 4 different tasks. I mean, obviously there can be more tasks. We're not doing any tasks associated with the graphical structure. We're not doing link prediction. We're not doing node predictions, but still that can be a possibility. So when you do the graph text retrieval, using basically we want to compare between the unimodal and the multimodal, basically. So unimodal is you train these embeddings separately. You only put it through a graph encoder and put it through a text encoder, and then you obtain contextualized graph embeddings and contextualized text embeddings, and that's it. There was no cross-modal encoding. So that is unimodal encoding, and multimodal encoding is exactly having this much more layer. I mean, the layer size would be the same. It's just that the number of parameters would be the same. It's just that multimodal model has a cross-modal layer, and unimodal model doesn't have a cross-modal layer, but the number of parameters will be the same. So, and you can fine-tune all models for the graph text retrieval task on the from get-go, or you can actually pre-train with these 4 pre-training tasks and then fine-tune, right? And when you use the pre-training methods, then you can see like the multimodal model is outperforming all the other baseline models. Obviously, this is kind of given because we are actually training the models to find a matching pair. So this much is given. So when you actually look at some of the examples, so here we're using text to graph retrieval. So given a discharge summary, we want to find the most relevant admission graph. So it's like a search engine. And here, what the model returned is these are the top 3, top 1, top 2, and top 3. And unfortunately, this was the original pair. So this was placed on the second. So this is not exactly the perfect ranking. But still, if you compare the first rank 1 and rank 2, you can see that the contents are pretty much the same. So they both contain these diagnosis codes. So knee joint replacement, infections to infections and inflammatory reaction due to internal joint prosthesis. I'm not sure how to pronounce this. Anyway, so this is diagnosis 1, diagnosis 2. Same goes with diagnosis 2, and the procedure goes the same. So venous catheterization. So at least they contain a very much overlapping set of nodes. So I guess it's not too bad of a job. And this is the reverse. So given a query, given a graph, given an admission graph as a query, you want to find the most relevant discharge summary. And this is this is rank 1, rank 2, rank 3, all the way to rank 2000. And rank 1 is the original pair. So fortunately, this time the model got it right. So let's compare between rank 1 and rank 2. So rank 1, the diagnosis code, the rank 1. So I guess this is diagnosis code. So diabetic ketoacidosis and secondary to diabetes mellitus type 1, and yada yada yada. So, and see, you can see this about the same thing, like diabetic ketoacidosis, GERD bacterial vaginosis none. I'm not sure what this is, but at least the two. They are all based on diabetic ketoacidosis here. Again, diabetic ketoacidosis, and especially here, diabetes type 1 and DM type 1, they're the same thing. So at least all the high-ranking notes are very much similar. Medication prioritization, we'll just skip this. Not that much interesting. The performance is about the same with all the baselines anyway. So node generation is pretty interesting. So here, everything, all the models are doing a pretty good job actually. So the node generation is not that much of a. I don't think it's much of a tricky task because based on a structured input, you simply need to map that into an unstructured form. So I think that is why the models are doing a pretty much good job. I mean, all the models are doing a pretty good job, especially if you use LSTM as the text encoder instead of the BERT as text encoder. It is doing a slightly better job. But we can see how much of a good job the multimodal model is doing using some qualitative examples. So here, what's happening is that you put this much subgraph of the entire admission graph as the input, and try to see if the model can generate a proper discharge summary, especially regarding the medication section. So in the discharge summary, there was discharge medication. Yeah, there was discharge medication, right? There was a subsection called discharge medication. So we want to see if the model can actually generate a legitimate looking discharge summary based on this input. And so this is the original. So here, there's a lot of nodes here. So these are all the nodes information from this subgraph. So as I said, there should be multiple prescription nodes for a patient. And the patient that we've seen, like in the beginning of the class today, the patient had 21 prescriptions on discharge. So there should be 21 prescription nodes. So in that case, there would be a lot of nodes here, like a lot of prescriptions nodes, a lot of drug name nodes, a lot of drug dosage nodes, a lot of drug route nodes. So that's what we see here. So there's like the patient was prescribed vancomycin, vancomycin 1,000 milligram, and oxycodone, fentanyl citrate. What else? Like isoosmotic dextrose, vancobase, acetaminophen, zolpidem, whatever. Like there's like at least dozens of medications here, and the original matching text, original discharge medication subpart of the discharge summary is this, and this is the one that is generated by the multimodal model, and you can see that sometimes it's right, sometimes it's wrong. At least from you can see the length is different, so that much is. I'm not sure if that's a good thing or a bad thing, because obviously this amount of text is not capturing all the information in the graph. So this is a summary, and I think the model is actually trying to capture more than the original text. And let's see the content. So here, number 1 aspirin, that's the same, but it's that the numbers are different. So in the ground truth text, only 181 milligrams of aspirin was given, but here the model says 325 milligrams was given. And I'm not really sure why. I guess here the acetaminophen 325 is here, so that is why 325 is here. And I'm not sure where 81 is coming from. Oh, so here acetaminophen 81 is here as well. So yeah, I guess the doctor decided to write only 81 instead of writing all the acetaminophenes in the entire graph. And what else? So there's a clopidogrel. And there is also clopidogrel, and this is actually here. There's clopidogrel in here as well. So number 2 and number 3 are both clopidogrel. I guess that's kind of a mistake on the model part. It's just exactly. Is it the same? Yeah, it's exactly the same entry. So here number 2 and here number 3 are the same thing. So that's the mistake on the model part. Anyway, but overall, the model knows how to write discharge medication in the style of the original text. So based on structured information, right? And this part is a bit more. There's a question. Does tokenizer method influence the quality of generation? That is actually a good question. So I guess when you say tokenizer method, you mean like either using word-based or subword-based, and if so, if subword-based, like byte pair encoding or word piece or sentence piece. So theoretically, no. So no, actually no. Theoretically, no. I'm sorry. Theoretically, yes. So if your subword vocabulary is a bit more friendly towards medical text, for example, instead of breaking, let's see. So instead of breaking acetaminophen into ACE, TEM, INO, FIN, that would be a weird subword, right? Because obviously you want to break this into acet and aminophen, right? If that would be more ideal. Or for example, like oxycodone should be broken down into oxy and codone, not OX, YCO, DONE. So I mean that would be more natural. That would be a more natural way to break down a clinical or medical vocabulary. So that, because oxy means oxygen, right? And acet means like acid, like subgroup in whatever, like alcohol, acid, whatever. So like these names are derived from like Greek or Latin roots. So you want your subword like tokenizer to break those into coherent Latin or Greek units. And hopefully that would actually improve the performance. But weirdly, that is not the case empirically. Empirically, anything goes and anything works. Like if you just use BERT-based subword vocabulary, it still works well, even though BERT-based vocabulary doesn't break down oxycodone into oxy and codone. It breaks oxycodone into weird little units. Still, it works well, and I guess it's because you're using such a gigantic model on top of the subword vocabs, subword tokens. You have like 12 layers of transformer encoder. So once you just put those into once the sequence of subwords go into 12 layers of transformer encoder, they just figure out the meaning anyway. It doesn't really depend on how nicely the words are broken down in subword unit. It all depends on the context. So I guess that is why it doesn't really matter. So the answer is theoretically it should influence, but empirically it doesn't. Yeah, hopefully that answers the question. Right, so moving on to the next one. So this time what we're doing is we're only putting procedure and diagnosis, this subgraph into the model and trying to generate the procedure and the diagnosis subsection of the discharge summary. So here we're seeing a little bit more interesting manipulation experiments. So this is the original nodes. So in the diagnosis nodes, there are 1, 2, 3, 4, 5, 9 diagnosis codes, and in the procedure there are 4 procedure codes. And the original text was PNA. This is pneumonia. So there is pneumonia here. So there's pneumonia here. I'm not sure what C. diff colitis is. I guess this is like Clostridium difficile is C. diff. What else? AFib. AFib is atrial fibrillation. So AFib is here. Paroxysmal. Is there a paroxysmal somewhere? I don't think so. So yeah. So the doctor wrote paroxysmal, but it's not. It is not in the structured graph. So there is information loss here. Pancytopenia. I don't see it here as well. Bipolar disorder. We see it here. Bipolar disorder is here. So it's not exactly one-to-one. As I said, they are complementary. For procedure, it says none, but obviously there are 4 procedure codes, but the doctor says no procedure. I guess there was no procedure of notice, like like noticeable value or worth noticing. So what happens if we make the model generate based on this structured information? So here it says pneumonia, C. difficile colitis, 3 atrial fibrillation, and 4 central. So central is weird. I guess that's a mistake on the model's part. I don't know where the central came from. Yeah, there is no word central here. Well, at least the pneumonia is right. C. diff colitis is right. Atrial fibrillation is right. Central, no. And the model also says none. So interestingly, the model understood that usually for these procedure codes, doctors don't write in the discharge summary. So that is why it decided to just ignore these procedure codes, even though they are there. So they're like venous catheterization. Catheterization is I'm not sure what is called in Korea. Catheter. It's like connecting your body with some. Let's see what catheter means actually. Catheter. So it's in Korean it's 도뇨관. 도뇨관. So it's like 오줌관이라는 거죠. But it doesn't have to, 그러니까 꼭 도뇨관 아니 캐테터는 도뇨관이 아니라 캐테터는 보통 이렇게 몸에다 이렇게 넣어서 이렇게 액체를 빼는 걸 다 이제 캐테터라고 하니까 꼭 오줌을 뺄 필요는 없잖아요. 뭐 수술한 다음에 고름이 차면은 뭐 수술 부위에다 이렇게 갖다 꽂아가지고 뭐 고름을 뺀다던가 뭐 그럴 수 있잖아요. 아니 뭐 항암을 하면서 암세포가 이렇게 죽으면 뭐 그걸 암 때문에 이제 암세포가 있으면 또 막 여기 막 고름 차고 막 엄청 막 이렇게 뭐 물 차고 그러니까 뭐 폐에 물이 찬다 그러면 폐에다가도 뭐 이렇게 꽂아가지고 물 뺄 수도 있는 거고 뭐 그런 거니까 이제 캐테터는 그런 어떤 뭐 몸에 있는 액체를 빼는 걸 이제 캐테터라고 합니다. So anyway, so venous catheterization, arterial catheter. So venous is 그러니까 요거는 정맥에다 꽂았다는 거고 요거는 요거는 동맥에다 꽂았다는 거고 뭐 그런 거죠. 그다음 parenteral infusion of concentrated nutritional substance. Not sure what parenteral infusion is. This is basically you're just you're inserting nutritious material into the patient because the patient can't eat or whatever. And injection or infusion of oxazolidinone class. This is just simply inserting antibiotics. 그러니까 요거는 그냥 이제 뭐 음식물을 주는 거, 영양분, 뭐 포도당이나 뭐 그런 거 주는 거고, 요거는 항생제 주는 거. 그러니까 이렇게 다 전반적으로 이렇게 막 뭐 엄청나게 큰 수술이나 그런 게 아니었잖아요. 그냥 뭐 삽관에서 액체 빼는 거고, 뭐 영양분 주는 거고, 항생제 주는 거고. 그러니까 이제 여기다 안 적었을 거다라는 게 제 생각이고, 그거를 이제 모델도 대충 알아들었을 거다. 이제 요 정도는 안 적는구나 의사가. 그래서 나도 안 적는다. 네, 뭐 그런 거겠죠. Alright, so that's pattern well picked up by the model. And then so this is a bit more manipulating experiment. So here, what happens if you erase this specific node, which is pneumonia here, pneumonia organism. If we erase this node and make the model generate a discharge summary, what happens here? Pneumonia is no longer included in the discharge summary generated by the node. And what happens if you? So this is. It means that the model is basing its text generation. It's depending on text. It is the text generation process is depending on the structured information. So that is why the change is reflected into the final output. And here, what happens if you initialize with random values of graph? Like if you just randomize all the nodes here into like just random nodes, what happens here? It means then the model just generates garbage. It's all sepsis. So even the format is wrong. Before it was like 1 pneumonia, 2 this, and 3 this, 3 that, but here it's just all sepsis. So it also means that the model respects the structure of the graph. So if you just assign random inputs to all the graph, then it'll just generate garbage. So garbage in and garbage out. I think there was a question. Graph data diagnosis procedure, prescription data chronological order는 무시되나요? In this particular example, yes. So in Mimic 3, diagnosis and procedure codes don't receive any timestamps, as you're already familiar with, because you've already done project number 2. So diagnosis and procedures, they don't come with their own timestamps, but prescriptions, they do. So prescriptions come with the timestamp, but in this example, we only used three three columns, which is drug name, drug dosage, and drug routes. No timestamps. But in the future work, someone might expand this work to incorporate temporal information as well. So that would be a very interesting concept. But I'm not sure if that temporal information from the structured modality is reflected in the unstructured modality. So I'm not sure if that when doctors writing like a medication, discharge medication subsection, discharge summary, I'm not sure if they write it in a temporal order. Like just because this is number 1 and this is number 2 doesn't guarantee that this was prescribed first and this was prescribed later. There is no guarantee. So I'm not sure how the model would try to use temporal information in the structured modality. It's like an unguaranteed, it's like it's unpredictable. This unpredictable behavior. All right, hopefully that answers the question. Yeah, and just like we've seen in the vision text example, attention behavior. So see if the model can ground the text information to the graph information, or actually vice versa. You can see if the model can understand the node is see if the model can ground individual nodes to a textual information as well. So here, this part is the original text. Is just that is summary. We're only looking at the I think we're only looking at the discharge diagnosis subsection in the entire discharge summary. So text is all diagnosis codes. I mean diagnosis description, and graph consists of yada yada nodes. So here, acute kidney failure is a diagnosis node. Symptomatic human. This is also HIV. HIV is also another diagnosis node. Hepatitis is a 간염이니까 another diagnosis node. And so this part is all graph nodes, and this part, I'm sorry. This part is text, and this part is graph nodes. So here you can see a lot of fake, like empty nodes, like admission nodes, diagnosis or procedure nodes. As I said, these nodes themselves don't mean anything. It's the literal nodes that matters. So here, these are the literal nodes, and these are the subwords. So you can see again, like you can see that congestive heart failure is not really well tokenized, because congest should be like a one coherent unit, but it is or at least if you were to break down congest into 2 parts, it should be con and gest, because con means together in Greek or Latin, I forgot. Con means like together. Gest is like digest, jest, something like that. So, but anyways, as I said, empirically it doesn't matter. Anyway, so these are the subwords, and you can see that the word kidney, when you try to study where the word kidney is attending to in the graph modality, the strongest attention is given to this specific node, which is actually acute kidney failure. So it is doing a good job of grounding the text into a structured information. And the same goes with HIV. So the word HIV, which means the word HIV, see where it's grounded, and the strongest connection is given to this node, which is asymptomatic HIV infection status. So this is AIDS 걸렸다는 얘기죠. So this HIV text is tied to this specific node, which is doing a good job. Interestingly, it also has a strong connection to hepatitis. And if you're familiar with 이제 에이즈에 대해서 좀 아시는 분이라면 에이즈 환자들은 면역력이 약해졌기 때문에 이제 그 여러 가지 염증이 잘 걸리는데 특히 간염에도 잘 걸려요. 간염에. 그래서 이제 HIV 텍스트라는 HIV라는 워드 또 서브토큰이 서브워드가 이쪽 간염 노드에도 이제 아주 강한 그 연관성을 가지고 있다. 그래서 이제 아마도 그 수많은 텍스트랑 이 그래프 페어를 보면서 이제 얘가 스스로 학습을 했겠죠. 이제 HIV가 뭔지는 모르겠지만 당연히 모르겠죠. HIV를 아는 상태가 아니니까 우리가 뭐 모델한테 어떤 의학적 지식을 불어넣어 준 건 아니잖아요. 그냥 잔뜩 텍스트랑 그래프를 왕창 줬을 뿐이니까 여러 개 막 보면서 이제 어떤 코릴레이션의 관점에서 학습을 하다 보니 HIV가 적어도 요 두 개랑은 이제 밀접한 관련이 있다. 그 텍스트가 라고 이제 그라운딩이 이루어진 거겠죠. 모델 입장에서는 마치 저번에 뭐 풀면허리 뭐 이디마나 플루럴 이퓨전 같은 게 어떤 특정 픽셀 패턴하고 이제 연관이 되듯이 여기서는 특정 텍스트들이 특정 노드들하고 이제 연관이 되는 거겠죠. 네. All right, so I guess this is probably this is the end of the slide. So any questions so far? So this ends up the multimodality week, and next week we're going to look at the synthetic data set, synthetic data. So yeah, next week will be synthetic data week. All right, so if there are no more questions, I'll see you guys next Tuesday. Have a good weekend, and see you guys later. Bye-bye.